In our last topic, we have derived the equation of motion for the damped vibration system. And after that, when the system is going to be vibrating differently, that we are going to be characterized with the help of the damping ratio. The damping ratio here, the epsilon, we are going to be showing. The epsilon is going to be greater than 1, then we can say the system is going to be subjected to the over damping system. When the epsilon is equal to 1, we can say that is going to be the critical damping. When the epsilon is going to be less than 1, what we are going to say, that is going to be our under damping system. So today in this topic we are going to be discussing about the under damping system. So in this under damping system, as per our discussion here, the epsilon is going to be less than 1. Then the radical value is going to be c by 2m whole square less than equal to k by m. So then we can say the system is going to be subjected to the under damping system. So then, as we know that the roots equal to lambda 1 and the lambda 2, we already derived. In this case, what will happen? The roots are going to be the complex roots are going to be the imaginary values. So from this one, I am going to be simplifying. The I is equal to the square root of minus 1. With the help of this one, I am going to be taking from these roots minus 1 outside. So then what I am going to get is the lambda 1 is going to be minus epsilon plus I, the square root of 1 minus zeta square whole into omega n. Similarly, the lambda 2 is equal to minus epsilon minus of I, the square root of 1 minus zeta square, that's multiplied with the natural frequency equal to omega n. So once we are getting the lambda 1 and the lambda 2, we do have the displacement of the vibrating system. What is the formula we do have? That's x is equal to a1 e to the power of lambda 1t plus a2 e to the power of lambda 2t. So from this one, x, the displacement of the vibrating system we can calculate, and arbitrary constants a1 and a2 we are calculating by the initial conditions when we are assuming that the t equal to 0. So I am going to be substituting lambda 1 and the lambda 2 in this equation from here. So then further we are going to be developing that equation. So here we have seen the x is equal to a1 e to the power of lambda 1t plus a2 e to the power of lambda t. Already we had the lambda 1 and lambda 2. I have substituted in this equation. So then I got it x is equal to a1 e to the power of this lambda 1 value and plus a2 e to the power of lambda 2 values I have mentioned. So in this case we are doing the further simplification from this equation. So that's going to be x is equal to a1 into e to the power of minus epsilon omega nt. Similarly, the e to the power of I, the square root of 1 minus zeta square omega nt. So similarly, plus a2 is into e to the power of minus epsilon omega nt e to the power of I minus square root of 1 minus zeta square omega nt. We do got it. So I hope you understand. This is going to be, we are simplifying. As we know that e to the power of x plus y is equal to e to the power of x into e to the power of y. On this formula, I am going to be dividing this epsilon as well as this one I value. So then what happened? We got it that is x is equal to a1 e to the power of epsilon omega nt plus this parameter, and similarly a2 e to the power of 9. In this case, e to the power of minus epsilon omega nt and the e to the power of minus epsilon. This is the common terminology. So then I am going to be taking out from that positions and then we are going to be deriving further. So after we are getting the displacement in this way, then what I am going to do, I have common terminologies, I take it from that side, that is x is equal to e to the power of minus epsilon omega nt, that's the whole bracket, that's into a1 e to the power of this parameter, a2 e to the power of this parameter. As we know that the e to the power of ix is equal to, what is the formula we do have? That's the formula is going to be cos x plus I sin x we are getting. This is the one of the imaginary equations we have. And one more, e to the power of minus ix is equal to, what is the formula? Cos x minus I sin x. So by using these two the equations, we are going to be rewriting this part so that we will get the further equation, so that we are going to be simplifying this equation. So from this equation, by using these values, I have rewritten the displacement of the vibrating system, particularly in the under damping system, that's x is equal to I took out this common outside, and by using this e to the power of ix is equal to cos x plus I sin x, right? And thus I have written a1 cos x is going to be here. This is the x value. So thus I mentioned here the place a1 into I sin x we do have. I sin x. So that a1 I sin x we do have. Similarly, from this a2 value also we do have ix we do have. So that means a2 cos 1 minus omega, this is going to be the cos x, and then in this case we do have minus. So then this is going to be minus a2 I sin the square root of 1 minus zeta square omega nt. And if you are going to do the further simplifications, that's going to be x is equal to what the formula, e to the power of epsilon omega nt. So that's I'm going to be getting a1 plus a2, because we do have the common terminologies here. What do you say? So that's going to be a2 cos and a1 cos. So from this one, cos square root of 1 minus zeta square omega nt. Similarly, from this one, a1 minus a2. So because we do have the minus value here and here is the positive value. So then that's going to be I sin the square root of 1 minus zeta square omega nt. So this equation we are going to be further simplifying by considering this one, a1 plus a2 is equal to c1 for simplification. Similarly, a1 minus a2, that's I is equal to c2. Once we are going to be substituting the c1 and the c2 in this equation, so then what happens, this equation will going to be simplified. Once we derive this one, then we substitute it in this equation. That means x is equal to e to the power of minus epsilon omega nt. So that's going to be a1 plus a2, we consider that as a c1 for the simplification of that equation, that c1 is equal to cos x, plus we do have a1 minus a2 that I am going to be into I. So that I am going to be considered as a c2, that I substitute here. The c2 is equal to c2 into sin x. So from this one it is going to be very clear that the c1 and the c2 are going to be depends on the a1 and a2. These are going to be called arbitrary constants. These arbitrary constants we can define from the initial parameters or initial conditions of the vibrating system. The initial conditions here is null, the t is equal to 0. When the t equal to 0, then we can define these arbitrary constants. In this way, we are going to be deriving the equation for this under damping system. The total system, we have derived the displacement of the system only. So after the deriving the displacement of the under damping system, that is the amplitudes of the vibrations, then what happened here, we are going to be defining the frequency of the damped vibration system, that is equal to the square root of k by m minus c by 2m whole square. As we know, this already we call that as a radical. So then what will happen in this case, for the simplification, as we know that omega n is going to be the natural frequency of the system, that's going to be square root of k by m. And similarly, c by 2m for the simplification I am going to be called as the value a. So then these two values, if I am substituting in this one, that is going to damped frequency vibrations, that is equal to omega n square minus a square. This is the value we are getting. One, this is called damped frequency. So the damped frequency is equal to the square root of omega n square minus a square. So from this one, we can find out the time period of that system. As we know the time period of the system, that's going to be the time period. That is here, the damped time period, we are going to be saying. That I am going to say Td is going to be the time period of the damped system. Td is equal to 2 pi by omega d, I am going to be right. So in this case, what is the value of this omega d? So that's going to be damped frequency is equal to this value I am substituting here. The 2 pi, the square root of omega n square minus a square. As you know, omega n square is equal to be, here is going to omega n is equal to k by m. And a square is equal to what is that one? C by 2m. So these values we are substituting, then we are going to be calculating the time period for the damped system. And we have to calculate the damped frequency. This is going to be damped frequency, circular damped frequency. This is called circular damped frequency. Then we can calculate the damped frequency, that's going to be Fd, I am going to be saying. Fd that is equal to omega d by 2 pi. And further simplification, I am going to be writing here omega n square minus a square by 2 pi. That is going to be the FD value. So this is called damped frequency of the vibrating system. The same equations we can use for overdamping, critical damping or underdamping system of this displacement we are going to be using to find out the damped frequency. This way we are going to be solving the equations. So after the derivation of the displacement of the underdamping system, so that we are converted into a graphical way. As we know that x-axis is representing the time period and the y-axis is representing the displacement of the vibrating system. As you see that when the system is going to be got the initial displacement or the forced vibrations, then what will happen? The system is going to be it's displacing from its mean position. So that I am going to be concerned this is going to be the mean position or equilibrium position of the system when it is displaced. Then after certain time, then what happened? We are relieving that force. Automatically the system is going to be coming to the equilibrium position and then energy is going to be here. Can you see the initial cycle? So then what happened? This is the amount of the energy it has stored. So that's we are going to be say that is going to be energy stored within the system by the different form, that is internal energy. Then this is going to be the x2, and then when it comes to here, this is going to be the x3 value. Can you see x1, x2, x3? The slowly the energy is going to be, that means the displacement of the system is going to be decreasing amplitudes. So then what we are going to be say that we have drawn with the peak values of the like this. This curve we are going to be called exponentially decrement curve we are going to be say. Already we have discussed that the energy dissipation or the displacement dissipation of the system is going to be taking place by the exponential way, right? Exponential manner. That's way in this code. So in this case what will happen? If I am going to be taking, so this the constitutive two cycles of these amplitudes x1 and x2, the distance between the we are going to be called the time period, right? So this way we are going to be defining the time period. So this is the for the underdamping system. The same diagram we can draw for the critical damping and overdamping that already we have discussed. For this diagram I am going to be draw the critical damping is going to be like this. So this is going to be the critical damping. And similarly one more, it is going to become like this. So this is going to be, we are going to be called, this is going to be the overdamping. So in this case, what is this one? This is going to be your underdamping system, the curve we got it, the behavior of that system. And next one we are going to call, this is going to be the curved one at 2 and 3. So in this, the first one we have discussed about the overdamping system. So then what happened? The decrement is going to be taken in this exponential way. So then what will happen in the curve 2 when epsilon, this is going to be epsilon is equal to 1. So then this is going to be the critical damping, it's going to be. So it's moving like this. And similarly, the third curve is going to be showing in this way. That means from this mean position we observed that overdamping and critical damping, they didn't cross the mean position of the system. They are vibrating only the one side of the vibrating system. That means directly they are coming to the equilibrium position. But in the critical damping, then what happened? The both sides, that system is going to be start vibrating from its mean position. So then finally it will, both in this case what we are going to be getting, it's taking time. For critical damping, the coming to the equilibrium position, it will take less time compared to the remaining two. So this way we are going to be analyzing the vibrating system. This vibrating system, critical damping, widely using for the Bofors guns, like war tanks, the rifles. Then what happened? Once you fire the system, then it must be comes to the equilibrium position within the short span of the time. If I am using the overdamping or the critical damping, it will take a long time to come back to the equilibrium position. So that's why most of the time we are using the critical damping for this kind of systems is the critical damping. Thank you.